Welcome to the third lecture, Memory Addressing and Languages. So, let us know about the overview of memory organization. What is a memory? Memory is one of the most important subsystems of a computer that determines the overall performance. What do you mean by that? See, as you have seen in the previous lecture that we are storing the instruction and data in the memory. If your memory is slower, then loading the data from the memory will be slower. So, in that case, we need to have a good speed memory. So, conceptual view of memory is, it is an array of storage locations with each storage location having a unique address. So, it is an array of memory location. So, it's an array of memory location. So, we have first location as 0000, next location as 0001 and so on. Maybe the last location is 111 and 1. Okay. So, it is an array of storage location, each with a unique address. So, this is a unique address. Unique address is associated with each of these locations. So, these are individual locations and this is the address associated with each of this location. And each storage location can hold a fixed amount of information. It can be multiple of bits, which is the basic unit of data storage. And a memory system with m locations and n bits per location is referred to as an m cross n memory. Both m and n are typically some powers of 2. So, these are some example 1024 cross 8. So, if I say 1024 cross 8, so 1024 means we have 10 bit in the address. We have 10 bit in the address and each of these location is having 8 bit. This is 0, 1, 2, 3, 4, 5, 6 and 7, 8 bit. So, how many locations are there? 1024 locations are there and each location is having how many bit? 8 bit. So, you can store these many locations, in these many locations you can store 8 bit each. This shows how a memory will look like. Now, some terminologies you must know when we talk about memory. What is a bit? We all know a bit is a single binary digit, either 0 or 1. Nibble is a collection of 4 bits. Byte is a collection of 8 bits. And word does not have a unique definition because we can either have a 32-bit word length of a computer can be 32-bit, word length of a computer can be 64-bit. So, word does not have a unique definition. Now, let us see how is memory organized. Memory is often byte organized. So, we never say that each bit is having an address, rather we say each byte is having an address. That means, memory is often byte organized. Every byte of the memory has a unique address and multiple bytes of a data can be accessed by an instruction. What do you mean by multiple bytes of data can be accessed by an instruction? So, I will just take an example. I took an example like add R1, LOCA. So, if you consider this instruction, it is depending on how many bits this add will have, how many bits this register will have, and how many bits this location will have. This will define that how many words this instruction will have, or how many bytes this instruction will have. So, in that sense, what I am trying to say is that how many bytes this instruction will take is dependent on various other factors, like the total number of instructions available in your computer, the total number of registers present in your computer, and also the number of locations you are having, based on which you can have the what will be the number of bytes required to represent this particular instruction. For higher data transfer rate, memory is often organized such that multiple bytes can be read or written simultaneously. This is basically needed to bridge the processor memory speed gap. We shall of course discuss this later, but I will just tell very briefly about this memory processor speed gap. So, as you know that processor speed is increasing, memory speed is also increasing, but not at the space the processor is increasing. So, this picture will show you the processor memory performance gap. See, with technological advancement we can see that that both processor speed is increasing and also memory speed is increasing. However, there is a speed gap. So, there is a speed gap which is steadily increasing. So, in between this gap is also increasing. So, earlier the speed gap was much less, but now with technological advancement, CPU speed has increased to a great extent. Memory speed has also increased, but not at the same space as your CPU. So, we can see this. So, some special techniques are used to bridge this gap. We will see this in the memory module design, where the concept of cache memory and memory interleaving will be talked about. But from this we can see, what we can say is that there is a still huge gap between the speed of a processor and speed of your memory. So, this is where we have to agree upon that we are still in the phase, we are growing, we are trying to make certain techniques to bridge this gap, but still this gap exists. Now, how do you specify memory sizes? Memory sizes can be 8-bit, which is a byte. It can be kilobyte 2 to the power 10. It can be megabyte 2 to the power 20, gigabyte 2 to the power 30, terabyte 2 to the power 40, and many more like petabyte, exabyte and zettabyte. Now, you see, if there are n bits in an address, the maximum number of storage locations that can be accessed is 2 to the power n. Let us see this with a small example. We will take n equals to 3. So, for n equals to 3, we can say that how many locations we can access? 2 to the power 3, that is 8 locations we can access. So, the first location will be 000, the next location will be 001, next will be 010, 011, 100, 101, 110 and 111. So, with n bit we can have 2 to the power n locations that can be accessed. So, by this what we mean, if there are n bits in the address, if we have n bits in the address, then the maximum number of locations that can be accessed is 2 to the power n. So, if we have 3 bit in the address, so maximum location that can be accessed is 3 cross 8. So, 8 locations can be accessed. So, for n equals to 8, 256 location to the power 8. For 16 to the power 16, that is 64k. N equals to 20, 1m locations. And for n equals to 32, 4g locations can be accessed. So, this diagram shows the address bit. If we have n bit address, we can have 2 to the power n locations that can be accessed. And modern day memory chips can store several gigabytes of data. That is our dynamic RAM. We will be looking into more details about each and every aspect of memory module, memory in memory module. Now, as I said, for an 8 bit, 2 to the power 8 unique locations we will be having. The first location will be all 0, all 8 zeros, and the last location will be all 1s, and each of these locations again will have some content. So, an example 2 to the power 8 cross 16 memory. So, in each of these 2 to the power 8 location, every location will have some data which is 16 bit. That is what is shown here. Some examples. So, let us see, a computer has 64 MB of byte addressable memory. How many bits are needed in the memory address? As I already said, that 64 MB. So, this is 2 to the power 6, 64 is 2 to the power 6, MB is 2 to the power 20. So, the address space will be 2 to the power 26 bytes. If the memory is byte addressable, then we need 26 bits to represent the address. Now, let us take another example where we say a computer has 1 GB of memory. So, we are saying total of 1 GB of memory. Each word in this computer is 32 bit. Okay. So, 1 GB, that is 2 to the power 30. Zero to 2 to the power 30 minus 1. So, we have total memory, each word in this computer is 32 bit. Now, this will change. If each word is 32 bit, that means this is 8, 8, 8, 8. So, this is 32 bit. Now, total we have, total address space is 2 to the power 30 byte, and if individual word is 32 bit, then how many total words are possible? 2 to the power 30 divided by 4, that is equivalent to 2 to the power 28. So, 2 to the power 28 words will be possible. Thus, we require 28 bits. So, this will change from 0 to 2 to the power 28 minus 1. So, it will not be 2 to the power 30. If it is byte addressable, each byte can be accessed, then it will be 0 to 2 to the power 30 minus 1. Now, each word is 32 bit. As each word is 32 bit, we have 2 to the power 28 words that are possible, and to represent 2 to the power 28 words, we need 28 bits in the address word. Now, let us also understand what is byte ordering convention. Many data items require multiple bytes for storage. and different computers use different ordering convention, data ordering convention. It is known as low order byte first and high order byte first. So, these two are called basically Little Endian and Big Endian. So, you see this data type character is 1 byte, integer is 4 byte, long integer is 8, floating point 4 and double precision is 8. Thus, if you have a 16-bit number which is represented like this, so in one way this is the total number, high order bit is stored in high order address and the low order is stored here and so on. Here it is stored differently. This is stored first and this is stored next. So, let us see the two conventions that have been named as. One is Little Endian. The least significant byte is stored at lower address followed by most significant byte. So, Intel processors, DEC alpha, they all use Little Endian method, where again I repeat, least significant byte is stored at lower address. Now, same concept follows for arbitrary multi-byte. So, if you also want to store multi-byte, then the same thing will follow there also. Now, Big Endian, the most significant byte is stored at lower address followed by least significant byte. So, the most significant byte is stored at lower address followed by least significant byte. IBM's 370 mainframe uses Big Endian concept. Now, let us see this representation with this example. So, a 32-bit number both in Little Endian and Big Endian. So, this is the number and lower byte is stored in lower address, then the next byte, then the next byte and then the next byte. And here the higher order address, higher order byte is stored in lower address, then the next byte, then the next byte and then this one. So, just see the difference between these two. In Little Endian, what we are storing? This is the least significant byte, we are storing in the least address, that is 2000, and then the next one and next one. In the similar way, the most significant byte, we are storing it in the lower address and then so on. Let us see memory access by instructions. Now, as I said that the program instructions and the data are stored in memory. So, there are two basic ways how this can be stored. One is von Neumann architecture. They are stored same in the same memory. Both the program and the data are stored in same memory. In Harvard architecture, they are stored in different memories. So, for executing the program, two basic operations are required. What are the two basic operations? We need to know this. Load the content of specified memory location. So, load R1, 2000, what does it mean? Load the content from memory location 2000 into R1 into this processor register R1. Another one is store. Store means store the content of R3 into this specific location, that is 2020. One is load, another is store. Load means load from memory, store means store into memory. So, either we load a data from memory into one of the processor register, or either we store the data from processor register to some location in memory. So, these two are performed using these two basic operations. Now, let us take an example. Suppose we need to execute this particular instruction. We need to compute this. What is this? S equals to A plus B bracket minus C minus D. I have to execute this in a computer. How will I execute? And all these S, A, B, C and D are stored in memory. So, what we need to do is, we need to load individual data, that is A, that is B, and then only we can execute it. So, let us see what are the steps that are required to execute this. First of all, let us first do A plus B. For doing A plus B, I need to load first A into some processor register, B into some processor register, and then I can add it. So, load R1 comma A will load the content of A into R1, load the content of B into R2, add it. Now, both R1 and R2 are processor register inside your processor. You can add them. You add the content of R1 and R2, store back in R3. So, this portion is done. Next, I move on. I load C into R1 and I load D into R2. Then I subtract D from C and then I store the result in R4. Now, A plus B is stored in R3, C minus D is stored in R4, and now I need to subtract it. What I do? I do sub R3 comma R3 minus R4, and my result is stored in R3. But finally, I have to store the result in another location, that is S. So, what I should do? Now, I have to store the content of R3 into S. So, I do perform an operation called store, where this particular instruction will store the content of R3 into S. So, this is an example how load and store operation can be performed, how these two instructions can be used to perform certain operation. Now, let us also understand what is machine level, assembly language and high level languages. Machine language is native to a processor and it is executed directly by an hardware. So, instruction, it only consists of binary code ones and zeros. So, I have talked about this, if you remember, that let us say this is my instruction. Again, I take the same example R1 comma LOC A, and as I said, this can be 1001 5-bit, this can be a 4-bit number, and this can be a, let us say, a 12-bit number. So, what I am specifying? I am specifying the entire instruction in a bits of zeros and ones. So, when I specify an instruction in the form of zeros and ones, where this number actually specifies add instruction, this number actually specifies this R1 register, and this number specifies this location. This particular way of representation is called machine language, which is native to processor, executed directly by hardware. You need not have to perform any other thing, you can directly execute this particular instruction. Next is assembly language. It is also a low level symbolic version of machine language. Now, instead of this, I write it symbolically, that is add R1 comma LOCA. When I represent something symbolically, that means this represent symbolic representation of the same instruction, both are equivalent, this is equivalent to this. but only that instead of writing zeros and ones, I am writing it with some mnemonics. And what are the mnemonics? This represent add, this represent R1, this represent location A. So, this language is a low level symbolic version of machine language. One-to-one correspondence with machine language is there. Pseudo instructions are used that are much more readable and easy to use. What do you mean by much more readable and easy to use? That means, of course, it will be difficult for me to remember 0110 is add, but it will be very much easy for me to remember this one is add. So, I can write an instruction add R1 comma R2 mul R2 comma R3 and so on. But for me it is not very easy to remember what is the code for add, what is the code for mul and so on, and what is the code of individual R1, R2. So, this is much easy way to represent a program, and to remember this is not easy. So, assembly language is nothing but some kind of one-to-one correspondence with machine language is there. So, we represent it with some mnemonics. Next comes to high level language. Now, you see, if you have to add 10 numbers or you have to sort some list in an array, you need to perform certain operation. Again, writing such kind of language where we say that for sum of 10 numbers you have to initialize it and then you have to repeatedly add it. So, there will be set of more instructions that are required to perform an add operation. Rather, for adding 10 numbers I can very easily write, let us say for I equals to 0, I less than 10, I plus plus, sum equals to sum plus a of I. Let us say in that array you have stored the result. But this is a representation in high level language, where we are adding, let us say in an array, A is an array which consists of some values and I uses for loop to add this values 1 plus 2 plus 3 up to 10. But to write the same code, I have to use set of some more assembly language code to execute this same instruction, same job. So, this is much more easier to code than this and than this. So, generally high level languages, basically the programming languages like C or C++ or Java are used, which are much more readable and closer to human languages. So, we can write a program in a high level language and that can be executed by your machine or that can be executed by your computer. Now, if you have to execute a high level language, then you need some kind of translator that should translate your high level language to assembly language or machine level language. So, these are the two things which are required. One is assembler that translates an assembly language program to machine language, and compiler translates a high level language program to assembly or machine language. So, the translation is done by compiler directly, or the compiler first translates to assembly language and then an assembler can convert to a machine language. But ultimately you need to have machine language code to execute your instruction. So, any high level language you write, ultimately you have to boil down it to machine language. That can only be understood by your computer. So, as I said, this compiler, you have high level language and then you can directly have a compiler that will generate an assembly language, and then that assembly language will be fed to an assembler that will generate a machine language, or directly you can have a compiler that will generate your machine language. There are the two alternatives that happens. Now, you can also have something called cross assembler or cross compiler. What it does? Like the compiler or assembler may run on a native machine for which the target code is being generated, or can run on any other machine. That means, let us say an example where you have an 8085 cross assembler which is running in your desktop machine, and what it generates? It is generating some 8085 machine codes. So, the machine codes which are getting generated by a desktop PC. So, this is a cross compiler. Similarly, an ARM embed C compiler which is available online may be running on a desktop PC, which then generates what? An ARM machine code for the embedded development board. So, we are writing a code in a particular language, there is a compiler which is converting it sitting in some other machines. So, this is known as cross compiler or cross assembler. So, by this I will end lecture 3. So, in this lecture what we have discussed is how memory is organized, what are the ways to store the data in the memory, and we also looked into that how an instruction is actually getting like what are the steps that are required to transfer an instruction from one level to another, like from high level language, how it is converting into machine language through some compiler, how from assembly language it is converted into machine language, and what is a machine language. Thank you.